We have to do evaluations for this course. One is university based, which is on D12. So please do that if you believe in such an activity. We also need to do the department survey, saying evaluation, and I need a volunteer for this. Like we finished the class, let's say about 10 minutes early today. And you're distributed. I have a leave. You're distributed, collect it again, give it to the department. So anyone can volunteer. Thank you very much, Shari. And pass on one to Mass also. So hopefully he'll be.
I can do his evaluations.
Okay. We said that we are going to not have class on the regular time on Tuesday. Instead, have it at 9 o'clock at night. I realized that I have a second dinner on Tuesday. So the request is, can we have it on Monday, 9 o'clock? Let's assume Mal also says a yes. By any chance, if he says that if he's not available, then we try for Wednesday or Thursday or Friday or one of the days.
Never.
Huh?
Or never.
No, that's right. It's a kind of a cool thing. But I never had a class, official class at 9 o'clock, I suppose. Have you guys ever had a class at 9 o'clock of the night?
No.
Okay, so it's first, okay, try that. So, okay, so. What else? There was a concern about, I put zeros for the homeworks. That is just from my organization sake that, okay, this is not submitted yet, and so on, so. It doesn't really mean that you cannot submit, you should submit. And, if you missed any homework, I don't think anyone has missed any homework yet. Keep submitting even if it's a sleep. Homework 13 is due. Oh, here it is. Second. Miles here. So the discussion was that we talked about having a class at 9 o'clock on the evening on Zoom on Tuesday. But it turns out I'm not available at that time because I have second dinner. I'm very popular.
So you're worried about us not being available, but you yourself.
Yeah, I'm not available. So my apologies. So I was wondering if you are available on Monday, 9 o'clock in the evening.
Next Monday,
Next Monday. Correct.
I believe so, yeah.
So unless you're not available, we'll have the class at 9 o'clock in the evening.
I can double check.
How many more sessions do we need to finish the course material?
2 more, like that's all. I mean, we can do as much as long as we want because I'll be pretty much compressing the scattering that we do
Let's do it.
in a reasonable manner in 2 lectures.
How many do we need to finish that everything?
I didn't understand.
How many?
You mean how many lectures do I mean? One on Tuesday and one on Thursday. But that's already compressing a lot.
So you're covering everything.
Yeah, like in a reasonable manner, give an idea. It's like saying antenna that we are doing can be done in a whole semester. But then you give the basic idea. That is also.
So we're not missing anything.
We won't be skipping anything, yes. Yes. Is this you submitted today, this one?
Also, yeah, I'm available on Monday.
Okay. Good. So. Yeah. Tuesday. on May 1, Monday, 9 p.m.
And the exams also due the same day, right?
Oh, yeah, the exam is also due same day. Homework 14 is officially due May 5. And the take home will be made available next week, hopefully early, if not like.
For the final.
Yeah, did I say something else? Sorry, the final exam will be mostly a take home with one question or so during the exam.
What would be the format of the in-class question?
Something very straightforward, you should be able to answer it right now. There's something that you should know,
So first, it'll be more like conceptual.
very conceptual, yeah. Like what's the Maxwell's equation, the fourth Maxwell's equation, something like that. And your equation sheet is allowed, so if you have it on the equation sheet, it's also good. So. Like one of those quizzes, sometimes I ask, sometimes I ask what is the dimension, something, how about this, we will find out the dimension of something. Like dimensional analysis is reasonably straightforward, like all of them. You'll ask for the dimension of some quantity, some reasonable quantity, like radiation impedance, nice quantity. Now I have told it, so I can answer that. So.
And it technically summarizes all the topics in the course, so.
No, technically it will not summarize, but it will make you study. Just because there is one question, the idea is that you will have to study for the whole thing, or at least you feel like, right, let's go through the notebook, and that's the basic idea.
Have you intended this one question or two?
I haven't. One or two, let's, yeah.
How about the take home part?
Take home part will be one question which will be very long. Which doesn't matter, right? It's most of the take homes are like that, one concept. I'm hoping I will do what is called optical theorem. But not necessarily, more recently, I was also thinking. Like radiation coming from atoms, what is the SPD dependence? Like whether it is in S state, P state, D state, how does the radiation change? So I was thinking that also, but yeah, depends how much time I spend eventually. Okay. Oh, one more thing. Today, first of all, we finished early because of the evaluations, and if possible, I need the computer also early. There is a talk by one of the grad students here in the math department, the corporate seminar. If you guys are available, Jared, yeah. So it's being presented by a grad student here. That's Dustin. So it's in room 380, no, room 286. No.
Isn't that the same?
386, yeah, room 386. Yes. So if you're available, check it out. Yeah. So this is something he has been working on his own. It's not related to his research area that he's actually working in a lab. So this is just on his own. He came up with this. So it's kind of cool. Yeah, so good to check out. Okay, so we are doing radiation and frequency domain, like frequency detection, frequency. Or mainly what we are saying is what's the color dependence. When something radiates, what's the color dependence? How much red light is radiated, how much blue light is radiated, how much ultraviolet, how much infrared. So we said we already did last time. Remember Fourier transform of So when you say frequency dependence, generally it is time dependence. You're saying now it's frequency dependent, wherever there is time, you're talking about frequency. Now, the moment you do that, the dimension of this quantity changes. Right? If f of t has dimensions, Fourier transform is e raised to e, right? I omega t e t minus infinity plus infinity f of omega, and it's minus omega t f of omega is equal to f of t. These are not the same functions. They should be, one should be tilde and the other one should be normal function, but I get lazy and I stop calling that a new function. It will be understood that whenever it's an omega dependence, it's a different function. Clearly, f tilde dimension is equal to time times the dimension of the function f, right? Exponential of the function. Also notice if you're doing Fourier transform in one space dimension, this will be f of k. This will be minus infinity to plus infinity. The x now Fourier transforming a function in x. This is equal to minus ikx and f of x. And again, make it f tilde. This is a new function again. This will be g if you want. And f of x is equal to dk over 2 pi. So that's your definition of Fourier transform I use. This is mostly there's a notation involved in different textbook, different people, same people in different fields. When you're working in quantum mechanics, when you're working in general math methods, you use different notations. Notice there is a plus here. When you're going from time to frequency, you use plus. When you're going from position to wave number, you use minus. That's not necessary. It's purely notational. If you start with this plus, as far as you make this minus, that's good enough. There's absolutely no strict rule there. There is a 2 pi here. There is no 2 pi there. It doesn't matter if you put the 2 pi there, and you're pretty good as far as you're consistent. It's like choosing a coordinate system. As far as you do the whole work in the same notation, that's perfectly fine. Even many times you will see 2 pi being divided between the two, square root of 2 pi and square root of 2 pi, especially quantum mechanics. There are features which make it very convenient in that case. And those are different notations. You use plus and minus here mainly to see the Lorentz feature coming in. Remember, kx minus omega t is a Lorentz invariant concept, right? So kx minus omega t. So omega t is here, kx is here. They should come in opposite signs, right? That's again not should come in opposite signs. You keep it positive or negative, it doesn't matter. It's just convenient when you already make it Lorentz invariant quantity, then it's just nicer or something. You can see that it doesn't really care because I can substitute t equal to minus t. This is an integral. And if I substitute t equal to minus t, then the integration changes and you can make that minus. So that's perfectly okay. There's no such rule as to what it should be. With all that features involved,
Is it possible to change to convert f of x to f of t?
oh, you cannot. Maybe I should say this is a new function. G. Does that help? It's not the same. Is that a confusion?
So we cannot use twice Fourier transform.
I cannot, right? If it is t, usually it is a function will be like phi, right? So there is an x, there's a y, there is a z, and a t. So there's a position in x, y, z, and t. So you will do 3 k's. So this will become phi tilde of kx, ky, kz, and there is an omega. Right, but I can do only T to omega and keep X, Y, Z. That's what I've done here. Time is Fourier transform, position is kept the same. But each time I do that, this is the operations I'm involved in. Okay. And we showed that this is equal to pretty simple. It is in the radiation domain. So there is an e raised to IKR over R. And there is a rho charge density also in the Fourier transform, but now this is Fourier transformed both in position and time. This is only in position, but here this k is omega over c, and vector k is omega over c times Rf. Remember, radiation has to do with, there is a sample here, that's your R prime, and there's an R. Right, where you're very far away in the radiation zone, it's only the charge density, and not only the charge density, the Fourier transform in the frequency and the wave number space, that is what contributes to the electric potentials, electric scalar potential. Pretty much algebraic, there is no integration involved, so it's very straightforward. This seems to suggest that this is complex. Right? How can electric potential be complex? Like exponential of IKR by construction is complex. Electric potential, naively, is real, right? Electric potential is something that you measure on the lab. The voltage, that's real, right? Here it seems to be complex. Why? Because of the K space. Very good, because of the K space, because you mean Fourier transform. A quantity being physical doesn't mean the Fourier transform will be physical. Fourier transform usually is not real. It will invariably be complex because of the exponent. So this could be real, right? This could be real. This one will not be real because you're multiplying by that complex number, adding so many quantities, mostly it is not real. Okay. So then you can ask, if some quantity is real, how will you test it in the complex space? There must be some feature in the complex space or in the Fourier space, which will reveal the fact that, oh, in the position space, it was real. How does it look like? And it looks like, so if you put the condition that this is real, that means f of t star is equal to f of t, right? That property in the Fourier space, how does it look like? F of omega star will be equal to f of minus omega. Okay, so that's how real quantity looks like. A complex conjugate will be you'll call it an odd function. Right, so the negative frequency will be the same as this one. This is a quiz for you. Not the usual quiz where it is not necessarily doable. This is doable, very easily doable. So try to do it. It will be useful. I'm not going to test you on that. It will be. It's just an attempting question, but for your own sake, you should try to do this. It's a useful thing to know that in Fourier space, reality shows up as a complex conjugation feature. So this doesn't even have a dimension of voltage. What's the dimension of this quantity? This is electric potential. If it was time, this is voltage. Right? Dimension of this is voltage. Here. What's the dimension of this quantity? Multiply by time, right? So whatever I start from here, I'm here, right? So start from here, that voltage multiply by time, I get the dimension of this quantity. So this is not electric potential at all. It's in the Fourier space. It will have different units, so be careful about that. Same thing here, this is charge density. It will not have the dimensions of charge per unit volume. This is Fourier transformed in space and time. So again, quiz. What are the dimensions of this? Yeah, this is what I'll ask in the exam. Right, I'll ask for this dimensions, right?
Didn't we do that for the last quiz?
Did I do that? Oh, was that? Oh, okay, sorry. Bad. I don't even remember what happened in the last one. So, okay. So that's your electric potential in the Fourier space and how it's related to the charge density in the radiation zone. Not always in the radiation zone. A similarly is equal to, very similar, same idea, mu naught over 4 pi e raised to I k r over r and j of k omega. That's what we did. We also did a feature. We said that in the radiation zone, mostly a gradient operator get replaced with I times k, where k is omega over c times r hat. And time derivative gets replaced with minus I omega. So we elaborated on that last time. Once you have that, then we can immediately do what's magnetic field, right? So magnetic field, which is R P is gradient cross with a R of P. But I'm interested in the Fourier transform of this quantity. Like that here R omega will be, the prescription is take the gradient operator, replace it with I times k. Very algebraic. The calculus in the radiation zone is very straightforward. You don't have to take the derivative, you just have to replace it with some variable. A r omega is mu naught over 4 pi e raised to I k r over r times j of k omega. Remember, k is omega over c times r hat. This is a quantity which is direction dependent. Let's manipulate this a little bit. Let me write this as I omega over c times r hat crossed with mu naught over 4 pi e raised to I k r over r j k. Just the rewriting it in a certain manner. Let me put a C for the magnetic field so that it has the same dimensions as the electric field. The moment I multiply C with the magnetic field, the dimension of that quantity is the same as the electric field. So I had to put a C here also. I'm going to do various things. I'm going to put a negative sign. Okay, so we're going to collect this whole thing. And let me say I begin with mu naught C over 4 pi. That's my C that I multiplied. I exponential IKR over R, that's a radiation zone, 1 over R, which is what survives on the dome when you talk in terms of energy. So as far as the flux goes, that will cancel out. And then I have a minus sign, so I need to put that together. So it's minus I omega over C Omega, remember, has to do with time derivative, right? Every time I see an omega, I should think of it as time derivative in the real space, in the Fourier space. This is omega. So that's time derivative, rate of change of current density. The Fourier space. That you should connect with the time domain. In time domain, we should have time derivative of j, and this 1 over r used to be their exponential was not sure enough. And we used to evaluate it at the retarded time. Now there is no retardation in time, instead you're in frequency, but it's a lot more straightforward than there where you had to evaluate it retarded time and so. Okay, that's your magnetic field. Yes, but
How, like, the speed of light came into the these,
this one here?
Yeah.
I just multiplied it,
and shouldn't that be cancelled?
so that's the C,
Oh,
the C. Remember, this had the dimension of resistance, right? So radiation impedance. So that's a nice quantity to keep always in the expression for electric and magnetic. So we have magnetic field pretty much immediately, yeah.
so is the dimension of electric field?
Is what?
We not see your flow.
Is what?
Dimensions of electric.
No, mu naught C is the dimension of resistance, remember.
Oh. With I, it's gonna be down here. No,
No, this is mu naught C is unit is ohms. It's in fact, it is exactly equal to 299.792.458, right? That's speed of light, basically, ohms. And that's it, this is it. Okay, this ends there, it's an exact number in a sense. And it comes up because mu naught is 4 pi into 10 raised to minus 7, right? Divided by 4 pi times c. So these two cancel out, so you multiply speed of light by 10 raised to minus 7 to get this. Speed of light is without the decimal, you put in the decimal 10 raised to 7 times c. Okay. And that's a proper, and you have the dimension of resistance. This is also equal to 1 over 4 pi mu naught over epsilon. So okay, so that's your magnetic field. We need electric field. Also, similarly, so electric field and time domain is equal to a negative gradient of phi or p minus time derivative of magnetic potential, right? That's the definition of electric field in terms of scalar and vector potential. When we go from here to the frequency domain in the radiation zone alone, it's this. Is E of R omega is equal to minus I K, but I should immediately switch my phi to this quantity here. So that's your 1 over 4 pi epsilon naught and e raised to I K R over R rho of K omega, and this is plus I omega mu naught over 4 pi e raised to I K R over R J of K. Right. That's equal to, let me take a mu naught over 4 pi out. And that'll be taken e raised to I K R over R also out. Let me put a C also there. Just so that the mu naught C over 4 pi shows up. And whatever is remaining, I'll write it down here, so that's equal. So mu naught C I have taken out. This should be, help me. So this should be minus.
And
Yes, minus
you can
and
replace the
K
K
for-
K, yeah,
with WC.
yeah, good, yeah, so I omega over C times R hat. And mu naught, so there is a 1 over mu naught epsilon naught and then C. Right? And rho. In the K omega space, and then there is plus mu naught over this all on.
Isn't mu naught C equal to 1 over epsilon? Yeah? You can do
Mu
that.
naught C.
Oh, yeah, 1 over mu naught epsilon naught is equal to C squared.
Yeah. So this one, right? Then the denominator that will become 1. Is that okay?
No, you take
The
out
C
the
is
epsilon
cancelled
naught
out.
and you multiply by C, so mu naught C is 1 over epsilon naught.
Yeah,
1 over mu naught epsilon naught is C squared, right? C.
yes,
One thing
1
we can say.
over mu naught. C square is epsilon naught, correct? And what's the problem?
The C is cancelled out.
Is it 1
Is this
over?
wrong?
No, that's right so far, but I'm saying. you
Yeah, I
say-
cancel out, yeah, you mean to say this whole denominator is 1.
Yeah,
Yeah, correct. I agree. Yeah, good observation, yeah, so don't write it, so I'll do it in the next day.
yeah,
Okay. So, and there is a J, good? J, there you go. Good. Okay. Oh, I can take an omega over C also out, I guess. Yes. Right.
You know what? Let's do it in the next step.
Okay.
You can do it in the
Yeah,
next.
you can do it on the next step, yeah. Right. So we'll do it on the next step, yeah, okay. That's mu naught over C over 4 pi. E raised to I K R over R. And this all gone. And I omega over C, I want to bring it out. And put a minus also in front. Or here. Reasonable. Okay. This is correct. Something is missing, something is wrong. Yeah, something is wrong. I missed a C. Isn't it? Something. So this is R hat.
You take it omega over C, so you can keep 1 over mu naught epsilon naught C.
Is this correct?
There should be a C.
Yeah, it should be a C, with the R
A.
hat. Right?
Oh, that's what I'm
J.
saying. Oh,
Or
yeah,
J.
good. So this is, this C should be inside, is it? Good. Okay. Better?
I think so.
Yeah, now I'm good. Okay, that's what I was missing. Okay. And there's a minus sign, right? No, minus sign, right? Okay.
No, you take out the minus sign, so it's
Oh, so I
minus
took
J.
out the minus sign, so I could put it on
So a
the,
J should be there.
okay. Too many errors. Good. But that's not convenient, right? But remember, we have one more equation, charge conservation we used in time domain also, is d rho by dt. Comma t plus j of, this is all time domain. This played an important role when we were doing the time domain equation. And we want to write that in the frequency domain with this prescription, right? In the frequency domain, this is minus I omega rho of k omega plus I of k divided with j of k omega. And remember, this is all in frequency and time, so let me clarify that. This is k omega minus j of k omega. This is equal to 0. Which means that the rho is equal to rho of k omega is actually related to j. And that is equal to I k. Remember, k is omega over c. Over I omega. And so put a cc I omega over c. So that's the same as r hat divided with good. Remember, r hat is your observation point, right? Somewhere very far away, you're observing. That is the only independent quantity. Rest everything should go away. So we can put this in here, and our electric field has a slightly better structure, but still can be processed. Requires some processing, and that is mu naught c over 4 pi exponential IKR over R, and then there's minus I omega over C. So almost like this quantity here, and there is a J also, but I have to first replace this. So this is R hat. R hat minus of 1. That's not right like that. Started with J minus of J. What is that equal to? That should be a familiar operation. In the time domain also it should look like that. What is that equal to? Simplifies.
Can I just zero?
Oh, why is it 0? Is that
Wait, never mind.
why is it not 0? How about that? Since it's point. Why is it not 0? J and a J.
That's a dot product.
Yeah, J dot product, but again, you get a vector here. Why is it not 0? It's 0.
Is it zero?
How will you convince me that it is not 0?
R and J are not in the same direction.
R and J are not in the same direction, correct? So, J is here. And R is here. R dotted with J. Right? This is smaller usually, right? And then it is in that, J projected in the R hat direction is not the same as J, so they don't subtract out. But what is that equal to? That's a simplified expression there. Yeah,
Back cap.
yes, back cab, right? That's the same thing that happened in time domain. If you do R hat cross with J, this is equal to R hat dotted with J minus of J hat. That's just that. That's equal to then. Let me write it in that form. So R hat crossed with J hat. For J hat, I'm going to put that whole thing inside. So that's minus, no, there's one minus, right? So Oh. Not. C over 4 pi. E raised to I K R over R. Minus I omega over C. Times J. K. Omega. Correct. And then you see that, oh, that's very similar to my magnetic field, except that I'm missing a sign. So put in a sign here, or let it be like that, or maybe I should clarify that there is one more bracket, right? And this is nothing but minus R hat crossed with magnetic field. Radiation fields always satisfy your plane wave conditions. E crossed with R hat is B hat, B crossed with R hat is E hat, and E crossed with B is R hat, right? Always they satisfy that. So if you know the magnetic field, you basically know the electric field also. Right? You don't need any, so you once proved this in general for any source. And in your homework, you will do this for one particular source. You will do this for a current carrying loop of wire, and what's the frequency? It's called a loop antenna. So you do that for that. Given a loop, what is your J? And then you try to calculate your electric and magnetic field. But you're mostly interested in the power, right? What's the frequency? It's the intensity of the signal that you're usually interested in. It's not the electric and magnetic field that you usually care about. It's the intensity. So it's a flux of power that you want to talk about. And remember your conservation equation. This is URP plus divergence of what is S here? Plus J after the electric field is equal to 0. What is S here? Like that's X is the flux of
The.
U. Flux of U, actually, it's called a Poynting vector. So if I were to integrate over a volume, so if I integrate over the volume, that is not time, and no, integrate over the whole space, correct? So there is no R dependence in here. So this is an energy density, so I get total energy over time. So let's call it E is energy now, right? So E is equal to energy. So dE over dt, and I integrate this, that's equal to negative QR and plus. So we are doing the integral over the whole space. There's a boundary, it is a dome, and that's equal to negative. So I can make this negative on this side just so that this is the flux that is going on, right? So that's equal to dA closed integral dotted with S, and that's equal to surface integral, which is done on an angle. So this is a solid angle, and R hat dotted with S, R comma T. So we have energy per unit time per unit solid angle. We did this in the radiation zone is equal to R squared, R hat dotted with electric field in the RP, the time domain, crossed with the magnetic field in the time domain. But this is supposed to be H, right? The momentum of the flux is the H, so I had to divide by mu naught. Right, that's your Poynting vector that you guys find. I want to write this in terms of magnetic field. Replace this cross and dot. R cross E is nothing but the magnetic field, and multiply by and divide by C. So this is mu naught times C times magnetic field R comma T squared. This is what we did in the time domain. We did that. This is just a quick review of what we did there. Okay, any questions? Yes.
Is the E supposed to have a, this is a vector?
This is a
Or-
vector. This is an energy, so I'm using two. E is also the electric field, the same notation for energy.
Isn't U usually energy?
U is energy density.
Oh, yeah.
So I've used U for energy density. One possibility is that I use small u for energy density, so that's U per unit volume cube, so that's a possibility. But I think this is the only time we will be writing it.
Okay.
So if you really, it's confusing, just write it as energy. Right? Explicitly write that as energy, and then there cannot be any confusion. So energy per unit time per unit solid angle, but that's not what I'm interested in. I'm interested in energy per frequency per solid angle. Like we said, we are interested in the frequency domain. So we want to switch over from here to time. So how do we do that? First get rid of the time. So integrate over time. So when I get do the integration over time, this is energy per unit solid angle. So integrate over the whole time. This is independent of that. And this dt minus infinity to plus infinity. And I'm going to write this in two ways. So this is d of RT dotted with Cp of RT. It's a real quantity, so it's square of that doesn't require any complex conjugation in here. Okay. I'm interested in Fourier transforming this, Fourier transform here. So this is equal to square mu naught C P. Fourier transform is in the frequency integral shows up. This is d omega over 2 pi, that's minus I omega t. And this is now C of B r omega. That's one of the magnetic field. There's another one. So dot product. But now I have already used my frequency. It's another integral. I have to give it a new label, right? So this is the omega prime. So it's a bilinear combination. That's what you say when you do Fourier transformation. This is a correlation between the two functions. In Fourier transform, correlation functions have some nice features. So that's 2 pi e raised to again minus I omega t prime. Oh, no t prime, but same t. And this is C d r omega prime now.
E2 minus I omega prime.
Omega prime, thank you. That's omega prime. Very good. There's one integral that is very easy to do in this, and that's a time integral. The only place where the time shows up is the exponential. That is, what is that time integral equal to? Anyone? What is a time integral equal to?
1 over I omega.
No. Try again. This is t exponential. Now let me write this as I omega plus omega prime at this time. You tried doing this integral as 1 over omega prime, but then you have to evaluate it at the limits. Right? These are oscillatory functions. What happens at the limits? What is that integral equal to? Familiar integral.
If pi over something.
No.
Yeah. And evaluate it at, let's say, let me write it in this form, e raised to ax. How about that? Evaluate this when a is equal to 0. What is that equal to?
And just a e to the I.
Oh. If a is equal
Oh,
to
a is
0,
equal to 0. It's just.
it's integral of dx, and how much is that? X, and then the limits. It's infinity. It seems like it is infinity. Right. And if a is not equal to 0, it is oscillatory, and you're integrating oscillating functions probably will cancel out, right? So one has to be more careful because it is plus one, minus one, plus one, minus one, right? But one seems like this is equal to 0. That's something familiar? Right, delta function, right? So this is, for example, this is a delta function and it's 2 pi times the delta. Okay, so this is a 2 pi times delta function. Which means I can do one more integral now. Right. Delta function integrals are straightforward. Replace omega prime with minus omega, and 2 pi cancels out. So this is equal to r squared mu naught c minus infinity to plus infinity e omega over 2 pi, and c times b or omega dotted with c times b or of minus omega. Right?
If it is a delta one, shouldn't then be equal to 1 when we integrate to minus integral plus something?
No, this whole thing is delta function. An integral f of t delta function of t is equal to 1, or is f of 0. Correct? So this is a delta function, so this allows me to do this integral now, the omega prime. And so I can do one more integral. Whenever you get a delta function, one integral immediately collapses, or can be collapsed. And then it's a frequency now. I'm interested in frequency, remember, so now it's a frequency, right? Is that clear? Like, more exactly what you would do is that since there is this minus infinity showing up, you say, oh, that's not a completely correct. Just take this as L, take this as L, and take the limit L tends to infinity. First, you show that this is equal to 0 for a finite region, and then slowly increase it. So it's a very sensitive argument there. But using that, we get this. Once I have an integral, usually omega goes from minus infinity to plus infinity. But in most of the scenarios, we are actually the positive and negative frequencies are the same. The color when you associate with it is identical. So restrict our integration to 0 to omega to infinity, and that basically puts in a factor of 2, so it is 2 times that. So first of all, let me say this is energy per unit solid angle is equal to r squared over mu naught c times minus infinity to plus infinity the omega over 2 pi. Remember, somewhere here I said that in the complex space minus omega is what? In the Fourier space, f of minus omega is the same as complex conjugate of that, right? If it's a real quantity, if a function is real in the standard, in the time space, in the Fourier space, this will be a complex conjugate. So this means that this is a complex conjugate. If it's a complex conjugate, I get a magnitude square there, so it is C, but in this case, the magnitude is important because this is really complex. The magnetic field in the frequency space is a complex quantity. There's a real part to it and there's an imaginary part to that. Right? So that's what we have. And then change over to 0 over infinity. So this is mu naught C 2 times 0 to infinity d omega over 2 pi C times p or omega squared. I'm interested in per frequency, so this is energy per unit frequency per unit solid angle is equal to whatever remains, right? So it is R squared over mu naught C 1 over pi C times magnetic field or omega squared. Right now, the magnetic field is this here. So replace that with the magnetic field. So it's R squared over mu naught C 1 over pi. Now the magnitude square, R minus will not contribute. I'm squaring this. So R hat crossed with mu naught C over 4 pi exponential of I K R over R and minus I omega. Minus I will not contribute when I'm squaring. So that's a omega squared over C squared. And that's J or K omega, which becomes. For this magnitude of exponential IKR, 1, so this doesn't contribute. When I take the magnitude square, right? R square cancels with R square, so this cancels this. There is a mu naught C square, only one survives. So this is mu naught C over 4 pi. That's your resistance, if you want. There's a pi here, there's a 4 pi there, so there's a 4 pi square. And there's an omega square over C square, which is a reminder that this is out. Hold on.
4 pi square.
No, this is, I wrote this wrong, right? There's only omega over C there. The 4 pi here, 4 pi square, omega square, C square, and R hat crossed with J K omega square.
Shouldn't it also have an I?
The complex I,
Yeah.
like
Next to the,
the magnitude, right?
magnitude, right?
Right, I magnitude squared is 1. So that doesn't contribute. And that's your. That's a frequency dependence of the energy per unit solid angle per unit frequency. You should take the dimension of this. Right, what's the left hand side dimension? What's the right hand side dimension? I said I'll ask something on the dimension in the exam, so that's something a suitable candidate there. As to what is the dimension of the left hand side, what is the dimension of the right hand side, and is it all consistent or not? This is the energy. In your homework, what you do is that I give you a J. Basically, I say that there is a loop antenna. A loop antenna is just a current carrying wire, a circular current carrying wire. That's it. It has a radius A, and there is a current I that is going in there. So that is all there is to it. And then you try to find the Fourier transform of that current density. And the moment you find the Fourier transform of that, you know the radiation. How much radiation will be transmitted by in all regions. Right. That's all. Okay, that's your homework. You will do that. You will see that in homework. And I'll stop here. And that should give you the time for evaluations. And I should be able to take this computer with me so that I can set it up there. Or Manuka, you will bring it. This, or I'll find it out. But I'm not supposed to be here. That's my problem. I cannot be here when you guys are taking the evaluations.
I can bring it to you.
Yeah, can you
Your list.
please? Okay, can you do that? Don't delay too much because I'm supposed to carry it then. Okay, that's great. Thank you very much. And we meet on Monday and I have to ask you
Give this
Zoom.
Can you give this? I will fill.
Oh. Okay. Everything?
Only this one.
Oh, wait,
Yeah.
so how exactly would we turn in our quiz? For our next lecture?
Just tell me when we meet that whether you did it or not, and I'll take it on your test.
Go on Monday.
On Monday when we meet. Just tell me I did do the quiz and that's some reasonable. Depend on how
I'll
it's.
hold up the quiz in front of the camera.
Yeah, something, oh yeah, it gets recorded, right? You just show it on the front of the camera. Sometime during the meeting, show up on the camera and that's. That's good, but I'm not going to find search for it. The section, section 1. Thank you, Karin. And. Okay. Only one quiz?
We didn't have quiz.
Oh, he submitted one quiz?
That's that we didn't.
I didn't answer the quiz.
More questions, right?
So
That is
we already answered. That's why we are not.
We
going to-
technically
but-
answered the quiz question during class.
Oh,
Yeah,
so,
that's why-
so you don't want to have a quiz?
Some of us didn't write it.
Okay, is that okay if I would not count this?
Oh, yeah, sure.
Okay, so that.
Yeah, yeah.
Thank you, Mass. You should get a bonus quiz. I'll drop a lot of this, hopefully it's not giving more. Thank you very much. Thank you.
This is different from the one we get in our email, right?
This one,
No,
no, I think it's different.
Yeah, but so we have to do both then, right?
It's 16.0.
Well, no, it's 4, 5, 4, 5.
Oh, that's not. Oh, okay.
I should probably stop recording.